Okay, we have a pretty easy derivative and a pretty straightforward Taylor polynomial. We got the weird Lagrange error bound, but I'm going to try and prove to you that that's really not that bad right there. We can handle this. And then we got the Euler's method at the end there, which got a little crazy with the arithmetic, but also you didn't really need to do all that arithmetic because they accepted the answer like this. So let's just kind of go through it here. So we have a derivative, and then they're telling us to find the second derivative, and they give us a point. So what I did first, my first derivative, I plugged in this point. So at 1, -1, I plugged in those numbers for the x's and y's. I figured out my y prime at that point is equal to 2. So when I take this second derivative, I get a y prime up in my problem, I can just replace it with the number 2. So product rule. So first function times it by the derivative of the second, taking the derivative of y's, tag on the y prime, plus the second function times it by the derivative of the first. There's my second derivative, but I just need to find it at this point right here. So I'm going to plug the 1 for x, plug in the -1 for the y, and also for the y prime at that same point, the y prime is equal to 2. So that's what I did right there. Try it on your own. Try it with the arithmetic without the calculator there. But I just plugged in that point for the x and the y. And for the y prime, I plugged in the 2, did some arithmetic, and got that -9. Part B, second degree Taylor polynomial about x equals 1. So that's your center. That's like your C value. And then so I said the second degree Taylor polynomial. I did f of 1, f prime of 1, x minus 1 over 1 factorial, f double prime of 1, x minus 1 squared over 2 factorial. That's your main definition of a Taylor polynomial. F of 1, they gave us right here that that was equal to a -1. F prime of 1, that is when x is equal to 1, what is your derivative equal to? That's what we found right here in part A. That was equal to 2. And then f double prime of 1, that's your second derivative at the x equals 1. So that's what you found right here, which was the -9. And then that just sort of carries down, and then you're done with part B. So pretty straightforward Taylor polynomial there. All right, now the Lagrange error bound. Here's what the Lagrange error bound says. Is you're going to put the error is going to be less than or equal to the maximum of the n plus first derivative, and then it's x minus c to the n plus 1 over n plus 1 factorial. So it's just kind of like how you're doing here. You do to the first over 1 factorial to the second over 2 factorial. It's just to the next thing. So there's the next derivative, the n plus 1, and then the n plus 1 factorial right there. Now, here's what was super nice on this one. We're going to know this formula, and then notice they told us the third derivative is less than or equal to 60, which means the maximum of that third derivative is equal to 60. It might be smaller than that, but they gave us what that number actually is right there. So if you just kind of know that basic formula, and then that is the maximum right there. They didn't even make us take any derivatives or anything like that. They just flat out told us that. So it's like, do we know the Lagrange error bound formula right there? So I did check the rubric. You could just put the error. The error, remember, is just the difference between if I plug that number into the actual function and if I plug that number into the actual second degree Taylor polynomial, there's going to be a slight difference between those. And so you could write it like that, or you could just put error is less than or equal to that. So that's what we want to do, is put the error is less than or equal to that. So I'm going to use this Lagrange error bound, the maximum of that. So since I use a second degree Taylor polynomial, that means when I go n plus 1, that's going to be equal to 3. So that's what I got. I'm doing the maximum of the third derivative. This is 2 plus 1, so that's to the third, and then that's 2 plus 1, which is the 3 factorial on the bottom. So they told us what the maximum was. And then this is your C values. When it ever says it's about something, that's your C value. And then the second degree, that was your n is equal to 2 there. And then whatever number they give you to approximate it, like f of x equals something, f of whatever, that's your x value. So I just did like the 1.1 minus the 1. I did x minus c, so the 1.1 minus the 1. And then I had the 3 factorial on the bottom. And then that was just like 0.1 like that. Now, this will get you a like credit so far, but you can't leave your answer like this because it tells us to use it to show. You got to show that this approximation differs at most 0.01. So you have to kind of just simplify that one. I know some other ones I will forget some crazy arithmetic, we can leave it alone, but you have to make this connection to that 0.01 right there. So the error is less than or equal to that formula thing. And then this was pretty easy to simplify. I did 60 over 60, get the 10. 0.1 was 1/10. And so I just did 3 zeros there. So 10 over 1,000. That's just 1 over 100, which is nice because they typically make that work out pretty nice for us. That's the 0.01. So I just mentioned the error is less than or equal to that 0.01 right there. So just please know that formula. It seems like that seems to be popping up a little bit more frequently lately. So we'll do that. And then I did check the rubric because that's just some weird stuff. So what's okay to say there? You can put the error is less than or equal to 0.01, or you can put the error bound is equal to 0.01. I pretty much just always kind of do something like that. So the error could be that. It's kind of like give or take that, but that's like the maximum that it's going to be off by, where it could be a little bit less than that, but it's not going to be more than that. So that's why I always kind of put it like that. But that is what the error bound is equal to. But they said if you put the error is equal to 0.01, then they're not going to give you credit for that because it could be less than that. That's just like what the maximum that is going to be there. So they didn't want you to put that. So these are the two things that were acceptable right there. And so I'm just pretty much always trying to do that right there. So if we practice that a little bit and study that a little bit, it's really not all that bad. Especially when they give that to us. Now, if they didn't give that to us, then we would have to like take a third derivative and see what the highest point is over this particular interval. So I would plug in like the 1 or the 1.1 and see what's the highest value right there. All right, and then the last one was Euler's method, starting at 1, 2 equal sides go to 1.4. And so this was real weird with the arithmetic. Usually they make the numbers a little bit more doable for us, but you didn't have to do all this work there. So I'll show you kind of what I did. But there's our Euler's method setup right there, like we've been practicing. So start at 1, you're going to 1.4 with 2 equal steps there. So that means your delta x is 0.2. So go 1, 1.2, 1.4, and this is the y value that we wanted to obtain right there. So there's your initial point. So what you'll do is you'll take that, and then this column here is delta x times dy dx. So the delta x is 0.2. So I'm doing 0.2. And then I need to take this x and y, the 1 and -1, plug that into my derivative. So I took the 1 and the -1, plugged it into my derivative right there. And that's where I got the other two numbers, times 2 times 1. And then that's what gave me the 0.4. And then what you do is you add up these two numbers. So -1 plus 0.4 gives us a -0.6. And then that's your new y value right there. So now you're dealing with 1.2 and -0.6. All right, so here is where it got a little bit crazier without the calculator. But let me show you what I did, and then just mention that you could just stop right here. They had on the rubric that they would accept this answer right here. So what I'm gonna do, I need to take the delta x times dy dx. So I did the delta x was the 0.2, and then the dy dx I had to plug in 1.2 and -0.6 and for the x and y into this first derivative right here. So see, I plugged in the 1.2 and the -0.6, and then that was being squared, so I squared it. So that's what this would be. Now, let's say you didn't even get that. What you would do, though, is take it and add it to the -0.6. So if you take this expression right here and add it to the -0.6, they accepted that on the rubric right there. Like if you wrote that down, you got credit. All right. So I think that was worth a couple points. If you're starting off Euler's method correctly, doing the Euler's method properly, showing that you know that process and doing your delta x properly, you get a point for that. And then if you get to this point here or this point here, you'll get the other point there. Okay. So I just want to kind of to make you feel a little bit better about the arithmetic right there, because I would like to have the calculator on that one. But what I did, I converted things to fractions. That kind of helped me. So I kind of did that was 1.8. I thought that was like 18 over 10, which was 9/5. I thought that was 2/10, which was 1/5. And then this is 36 over 100, which I know that reduced to 9 over 25. So that's where I got the 81 over 2625. And then that was like -3/5 plus that. So then I got a common denominator, and then I was able to get that. Like that's really the y value right there. Um, but yeah, the insight I saw was that crazy. I checked that rubric, and they did have on there, you could just leave like this. But remember to include that -0.6. Like you're gonna do this guy and then add it to that. So just add up these two items right here and just leave that alone if that arithmetic gets a little bit too crazy there. But that's not too bad of a problem there, but we just kind of practice some of those weird things there. I think a couple of wrenches they try to throw at us on that one there with the Lagrange and making this a little bit weird, but it's good that we get exposed to that and that we're seeing that there. Premium gasoline. Premium.